Hello, in this video I'm presenting dynamic field of view restriction in 360 video, aligning optical flow and visual slam to mitigate visually induced motion sickness. My name is Paulo, and I'm a PhD student from the University of Lisbon, and this work was done in collaboration with Oakley from also National Institute of Science and Technology, and my advisors Valentina, Nisi, and Nunes from the University of Lisbon. Virtual reality has research as a medium for work and entertainment, but key user experience issues still prevent many users from enjoying VR. One of these barriers for adoption is visually induced motion sickness, sometimes referred as simulative sickness, VR sickness, or cybersickness. Visually induced motion sickness occurs strictly from visual stimulation. It's polysymptomatic, meaning that there's multiple symptoms, and polygenic, meaning that those symptoms manifest differently across individuals. Some techniques for symptom mitigation in VR include hardware improvements, creating vestibular responses, natural walking, and artificial locomotion interfaces. However, these techniques are not compatible with 360 video. For 360 video, techniques using visual optimization like independent visual background and restricted field of view have been shown to mitigate visually induced motion sickness. It is of interest that these techniques be designed to be less obtrusive, only being applied when needed. Therefore, in this paper, we present a method using a visual SLAM, a visual simultaneous localization and mapping system, to differentiate between when the camera is static and when the camera is moving, and use this to apply visually induced motion sickness mitigation only when there is movement. We then use optical flow, a motion pattern caused by the relative motion of objects compared to the camera, of the user's peripheral vision to determine the aperture of the field of view. We extended OpenVSLAM, an open source SLAM system for equirectangular videos, by making it compatible with videos with multiple scenes. We use visual SLAM as a way to differentiate between movement versus stationary. To test this, we manually classified a video with multiple scenes into three categories: stationary in green, slow in yellow, and fast in orange. Our automatic classification of stationary in movement is generally consistent with the manual classification. We use a gunner front-back dense optical flow algorithm and group those values into a grid. During runtime, if there is movement as detected in automatic classification, concentric rings of raycasters poll for optical flow values in the periphery of the field of view and adjust the field of view accordingly. Based on this implementation, we organize a user study comparing our dynamic field of view to two baselines: unrestricted, meaning that the field of view is at 90 degrees, therefore no vignetting appears, and fixed, meaning that the field of view is at 40 degrees and vignetting is constant. We did a within-subject study with 23 participants who experienced all three conditions. We also looked at a subpopulation of this group that was more prone for motion sickness. We adopted a mixed methods approach using self-reported data like presence and the similar sickness questionnaire, using semi-structured interviews, and using objective measures like head direction data. We highlight some of the findings. First off, looking at the dynamic field of view, there is a clear restricted field of view restriction applied to fast intervals in orange. This is expected since those intervals have higher values of optical noise. While the dynamic field of view is also applied to slow intervals in yellow, there's more variation and those values are closer to those than when there is no restriction. Regardless of the amount of field of view restriction, users had similar patterns of viewing, exploring the scene in stationary or slow scenes and focusing on the movement direction during faster scenes. Looking at how much the head moves between readings, participants who experienced the fixed field of view had less movement than unrestricted field of view, and the values for the dynamic field of view are closer to those of unrestricted field of view. Dynamic field of view was shown to be statistically effective in reducing or maintaining scores of the similar sickness questionnaire total score and nausea when compared to the unrestricted field of view for both the full population and upper 75 percentile subpopulation. As expected, participants experienced unrestricted field of view reported higher values for general presence and spatial presence compared to the fixed field of view. For the dynamic field of view, these values are closer to when there's no restriction. Dynamic field of view is noticeable as expected since it's the only condition where the field of view varies, but it was also mostly well accepted by participants in terms of enjoyability and comforts. From the semi-structured interviews, we point out some noteworthy aspects. Firstly, some participants report the dynamic field of view as distracting. We posit that this is mostly referring to slow scenes where there's an instability in the field of view size that may result in the creation of more optical noise rather than masking it. Secondly, some participants report dynamic field of view as being part of the experience or for attention guidance. This also makes sense because when dramatic changes in field of view size happen, it normally is when the fast movement starts, like jumping off a canyon. So it can easily be interpreted as a cinematic choice. Overall, although noticeable, dynamic field of view was mostly well accepted by participants, allowing for the exploration of stationary and slow scenes, and protecting the user from optical flow during fast scenes. In our paper, we also highlight future work like eliminating field of view instability in slow scenes that may be solved by a better distinction between fast and slow scenes, or by incorporating velocity estimation as an input. Finally, our results are promising, but further testing with different videos and longer durations is needed. This would help not only test the efficacy of dynamic field of view restriction, but also help to generalize it to all 360 videos.